How did you find the level of the problems? Were they too hard, too easy?
Oh, they were pretty hard.
They were hard, easy?
Drive it from
Both?
with MATLAB, it was easy.
Well, you used MATLAB?
Yeah.
Okay. Oh, on the last one.
Yeah.
Yeah. Yeah, I used Mathematica. And
or actually, I used Mathematica, and someone else used it.
I find Mathematica is a little bit faster to get plots out of.
Yeah.
MATLAB, the plots look a little bit better, but MATLAB is more like a language, and Mathematica is more like fun and games or something. I don't know. Anyway, I was actually a grad student with Steve Wolfram at Caltech at the same time. I knew him. Anyway. Okay. With that, why don't we get started? So again, today is our third class, and today we'll talk about Poynting vector and total internal reflection. So maybe first a couple of things. The grader is Kian Junani. He's one of my grad students. He'll have office hours. I put this in the syllabus and loaded the syllabus onto the website, so you can read this there if you want to, but just so you're aware, Kian will have office hours 1 to 3 on Monday and 2 to 3 on Wednesday. Those will be in ECEE 128, which you think would be next door to ECE 130, but of course it isn't. It's way around the corridor. I don't know what my office, which is 130, is next to. I think it's next to 150 or something. But anyway, that's the standard numbering system in the engineering building. That's not Kian's office normally. That's one of my other grad students' office. His office is down in my lab in the basement. So if it's not during office hours, you probably want to email him or call him or something, because my lab's down on the second floor in the basement. And even if you go down there, the door is far from the office. At any rate, also I posted the slides from the lectures. People wanted them, and they're on the website, the regular website. People have asked about a D2L website. I'm not keeping a D2L website. I'll keep this one that's on SCOF, that's on the department computer, which is open, which is one of the reasons why I won't post problem solutions on there, because that's not a password protected site, but you can email me and I'll send you problem solutions gladly. And I guess the other thing here is, like I mentioned, I plan to have students work the problems in class, and we'll start that on Thursday, this Thursday, so I'll email you to set that up. I think I will start doing that alphabetically. So I'm not sure who's first. I don't remember who's first on the list, but I'll assign 2 of you for Thursday and 2 of you for next Tuesday. And the idea will be to send me a slide or 2 of your solution, and I'll put that into the lecture, and then let you have the microphone, and you can stay up here and get a suntan or whatever from all these lovely lights in front of me. Okay, so with that, so again today, the topics are the Poynting vector and the irradiance, or the optical intensity, and we'll also talk something about total internal reflection. We won't talk about group index. This is left over from last time. I should probably erase that. We will talk about Snells Law. Okay, this is a picture from the last time to just remind you that when we have a z-directed plane wave, that means there are two polarization directions. And here we'll take the x direction. So the E evidently could be along x, it could be along y. If the E is along x, then the B is along y. And then we get E cross x, because this is the direction of propagation. We'll use that in a minute with the Poynting vector. So this could be E x by, or it could be EY, and then it would be minus bx. So if we were going that way, if we had EY, then minus bx would be the other piece of the triad. And we'd have, so if we have if EY were EY0 cosine beta z minus omega t, then bx would be minus by0 cosine beta z minus omega t, or kz. Okay. So with that, so the magnetic field, the magnetic induction, that is, if we use B, I'll probably slide back and use H. If you go back to Poynting's original paper, actually his original paper is quite interesting, even though it's from 1895. Back then, still nobody knew in 1895, 26 years after Maxwell wrote down his equations, people were still very confused about energy flow. And 1895 was the year where Hertz started transmitting radio waves over hundreds of kilometers between ships out in the Mediterranean Ocean. So it was pretty clear that electromagnetic waves worked, the wave equation worked, Maxwell's equations were correct, but people understood phase fronts and E fields and B fields and H fields. Evidently the del cross E equals minus dB dt and del cross H equals J plus dV dt, they were old. Faraday's law, Ampere's law, people had known those 100 years before. By the late 1700s, early 1800s, people had circuits, machines, all kinds of things like that, but it was the flow and free space that people didn't understand. So, and actually Oliver Heaviside, previous to Poynting, had been able to solve the problem of parallel transmission lines, wires, the twisted wire pair that were being used in telegraph systems. And actually, Heaviside was also the first one who wrote down Maxwell's equations in vector form. Very, very few people knew vectors back then. But Heaviside, who didn't have a college education, knew vectors. Maxwell, who was a Cambridge professor, didn't. But anyway, Heaviside was the first one to write down the Maxwell's equations we know. But he actually got fired for figuring out how a telegraph wire pair worked. He was working for one of the British telecom companies, and they had a couple of transatlantic cables that worked kind of, and then they were going to make a long one from the north of Britain to Denmark. And he went to his boss and said, "This isn't going to work, your design is wrong." If you look at he didn't call it the Poynting vector, but he was the one who said, well, look, on the outside of the metal, let's say this is the metal conductor. Said on the outside of the metal, the electric field is pointing out. So the electric field kind of looks like a porcupine. He said, well, at some given moment, the current's going that way. So there's an H field going this way. Let's call that HV, call that ER, and let's call that SZ, the Poynting vector along the Z direction. So he said, well, look, in the metal, the conductivity is high. at least at RF frequencies, the conductivity is high. As most of you probably are aware, the conductivity, or actually the epsilon, is the epsilon, the imaginary part of it's very large at RF frequencies. It's actually quite negative at optical frequencies. Optical metals don't conduct at optical frequencies. They're plasmonic rather than conducting. Only at radio frequencies is metal conductive. But anyway, as Heaviside told his boss, look, the sigma is really big, and that means that the charges inside of here can move around quite freely. So there isn't going to be any electric field inside the metal. There won't be any magnetic field inside the metal. It's going to be about zero. However, near the edges, you'll have really strong field. It'll be pointing up. So it was this model that Heaviside used, and he told his boss, look, don't spend money on the metal, spend money on the cladding material, spend money on the metal coating. And they said, no, you're nuts. You don't have a college education. You don't know what you're talking about. You're just a jerk. I'm not going to listen to you. And he came back with things that were much more vehement than that at his bosses. He was known for colorful language. I don't think he ever had a job again after that, even though he published more papers, has more awards, never did win the Nobel Prize, but has more awards than practically any of the people who were college educated at that time. He did that, I think this was the 1880s, that he did this with the telegraph companies. And they learned after that buy better insulator material for the cladding. Don't worry too much about the quality of the copper. It's not important. And we all know that, or at least the cable companies know that today, that you want to make this stuff really good. It wasn't until 1895, though, that Poynting was the one who did this, and his real reason was for antennas. So Hertz at that point was making these spark gap antennas. And when you get near to the antenna, nobody could figure out where the field was or calculate the radiation pattern from the shape of the wires. So it was really Poynting came up with the Poynting's theorem and the Poynting vector to try to figure out how energy was transported away from the antenna. With the plane wave, it was already pretty clear from, if nothing else, Heaviside's explanation. The twisted pair kind of looks like a mini plane wave. The only difference is at RF, because of the conductivity, you need to have a center conductor. If you go to higher and higher frequencies, you don't any longer need the center conductor. The plane wave doesn't need it anymore. Okay, so at any rate, with that, if we go back to the last slide or whatever, there's a relation between the electric field and the magnetic induction. We could write that as a relation between the electric field and the magnetic field that looks more like this. This eta over here, if you aren't aware, is the impedance of free space. If I'd wanted to put an n in, it would be eta 0 by n, or we sometimes write eta, the impedance of a medium, as epsilon r, epsilon 0. So this has dimensions of an impedance. The value of this thing here is 377 ohms. This is one of the reasons why we need transmission lines. If we're at very low frequencies, for example, we have a circuit, and we look at the wavelength of the electrical disturbance. If we have a circuit and we're operating at a megahertz, well, megahertz corresponds to like 300 meters. And the circuit, you don't have many circuits that are as big as 300 meters. So the wavelength's very big. So everything's equipotential inside of the circuit. There's no wave concept or anything. It's like a wave going up and down. Everything's always at the same potential on the inside of there. As soon as you get to the point, though, where the wave starts being comparable to the circuit dimensions, unless the line that you're on has an impedance that's lower than 377 ohms, you're going to be in trouble. Because the wave always sees an impedance of 377 ohms at infinity. And hence why we have 50 ohm lines and 75 ohm lines. You want the wave, which in those cases of using a 50 ohm line is small compared to the propagation length. You want it to stay in the wire. You don't want it to go the other way. And then you unload it when you get to the antenna at the end, and it radiates like crazy out of that. Okay, so anyway, that's a little bit of culture to go with pointing. So these are the equations, the relation of E and B. So again, we have a picture that looks like this. E and B are propagating along. We'll talk about an area K propagation vector, area A propagation direction K, which we'll usually take to be Z. And let's find out what the energy flow is for this specific configuration. So what you find out from the plane wave is that the electrical energy and the magnetic energy densities are equal. So we find out something like this, that again, oops, why did it do that to me again? So let's do that carefully. So we talk about electric energy. The electric energy looks like something like epsilon over 2 the electric field dot the electric field. The magnetic energy density looks like mu by 2 the magnetic field dot the magnetic field. Total electromagnetic energy density is the sum of these two. And in our present case here, that looks like, for a plane wave only, that looks like twice the electric energy density. And now if we use B instead of H, we remember that B equals mu H. So we get the mu flipped upside down. Okay. And this is easy to work out. You just write down the wave equation. It's rapid to figure this one out. So we'll just take that as being known that those are the energy densities. So this would be the total energy density of an electromagnetic wave. So that's power, or that's energy per volume. Total energy per volume, joules per cubic meter. If we want to turn that into a power flow, so okay, so we've got, oops, why does it do that? I guess it doesn't do that if I hit pen first, or not as badly. So what we've got here is we have X and we have Y. And now if the wave is propagating along at a velocity v, then the distance z that gets propagated in delta t is something like v delta t. So the volume would be something like the cross-sectional area times v delta t. So if we say we have energy density, then if we say we have energy density is WE, if we say total energy, capital WE, is going to be that times the volume or is going to be A V delta T times AV delta T times little WEM. That's what this thing is. So this thing here is the volume. There's the energy density over there. So this is total energy. This is something like total energy. And then this over here is per area. That's WEM. That should be cap. WEM. And then down here is divided by the area, so then it becomes energy per unit area per unit time, which becomes power per area. Okay, so the Poynting vector is in units of power per area. For that plane wave, then it becomes this V E epsilon EX squared. We can write it in terms of that, or more in general, it becomes this over here. Okay, so that is the Poynting vector, something like V squared epsilon naught ER times that. Now, if we, let's go one more forward. That V should not be squared. As you notice, it's not squared over here. It's not supposed to be squared here either. I kind of thought that. So when we get over here, that's not squared. That velocity, right, if we remember, velocity should be equal to something like c divided by n. You might remember c looks like 1 over square root epsilon naught mu naught. If we then use this one in here, we can find out that this thing here looks like eta over 2 E0 squared. So we can write it as an impedance times a field, the square of a field. Okay, so that's the average power it's in an area. Is something like the electric field squared, the impedance times the electric field squared. We call that irradiance, or actually more commonly we call it optical intensity. Maybe somebody else calls it irradiance, but I wouldn't. I'd call it optical intensity. There's a thing called specific intensity. That's different. Specific intensity is the quantity that's always used in astronomy, astrophysics. It's also used, it's called brightness if it's, what do they call that, illumination science or illumination engineering. It's called brightness. But the specific intensity would be this thing here, would be the optical intensity into a unit solid angle. So you'll hear intensity being used, especially if you're talking with astronomers or illumination engineering. That's the name of the field. If you talk to those people, they'll talk about brightness or specific intensity. That'll always be per steradian. They're worried about the actual angle. But if we talk about optical intensity, it's only per area. We don't worry about what the actual radiation angle of it is. Even though that radiation angle is very, very important when we're trying to couple light between optical fibers or between a source and some kind of waveguide, the numerical aperture of the light coming out is actually the more important. The brightness is actually the more important brightness coming out of a fiber, but we normally then do things like use Gaussian beams or something. Okay. So average irradiance or intensity, and okay, that doesn't really add too much here. So let's think about some waveforms and what the actual optical intensity for those waveforms would be. So one of them are archetypical, one of the archetypical waveforms then would be the intensity coming out of a spherical wavefront. And as we saw before, that looks something like this. It's a power divided by a unit area, or by an area, would give us the intensity. So if we move closer and closer towards the source, the intensity becomes higher and higher and higher. But again, there's no problem with that. So again, if we looked at a spherical phase front, something like this, as long as we're looking into a uniform area, we're going to see the same optical intensity. Okay, that's also something that's called the brightness theorem. The theorem of specific intensity. As long as you keep looking back at the same solid angle, you'll be subtending the same amount of optical intensity, of intensity per unit angle. Of course, then what we come to more realistically is the Gaussian beam. If we try to actually generate some kind of waveform, we'll generally get a Gaussian beam if it's coherent. If it's incoherent, we'll generally get a Lambertian. But if we try to generate some kind of coherent light, this then becomes diffraction limited. One of the reasons why illumination engineers, astrophysicists, other people use brightness is generally the light is partially coherent. We'll talk a little bit more about partially coherent later. But there, for example, if you have an incoherent source, you put it through an aperture, you induce spatial coherence. So the coherence is always changing. If you have a telescope or a spectrometer that's looking at incoherent light, the spatial coherence is growing as you go through the various optical instruments, and you can end up getting nasty fringes and junk that you don't want where you don't want it because of that growth of the spatial coherence. Those of us who do optics in a lab, we're generally using coherent sources. We're using lasers and such. If you have a coherent source, it's always going to be coherent. It's always going to be temporally and spatially coherent. It's very hard. You have to have something moving with time to destroy the coherence. Otherwise, it's always going to be coherent. So if we have a coherent source that's coming out of a cavity, we can always describe it, if it's in a single mode, we can always describe it by something such as a Gaussian beam, as long as we're talking about one single mode of the field. If you have multi-modes, then you have another problem. But so this is a pretty good description of coherent fields. Of course, the other thing that we generally have in the lab is we could have an incoherent source if we're making organic LEDs or something and they're radiating out. But then we're generally just looking at them and we know that they're radiating like a Lambertian. We aren't doing the kind of things that illumination engineers are to try to control the solid angle. We generally aren't worried about that. We have one or two cases. We don't have the general case. Okay, so here again, reminding ourselves here, we have a Gaussian beam. There's some kind of waste that we call 2W0, not W0. At some point we come out here and it's root 2W0. We call that a Rayleigh range. And then we can talk about the intensity of this beam, which is going to be the maximum intensity, and then it's going to fall off in this Gaussian. and in general is W is a function of Z. And not only that, we know what that W is a function of Z. Looks a whole lot like that. So that grows as the square underneath the square root, diffraction limited. Okay, so again, that's our typical Gaussian beam. So if we want to put in that I max in order to find it, we remember that that I max is something like this. It's 2 times the power per the minimum area, or this would be the area in general. I guess that would be W. The waist is a function of Z. So again, power per area there. And again, we remember that the divergence angle is something like lambda divided by the angle of the beam coming out that way. So what we find out is that again, the maximum, we can write then the intensity in terms of the we can write the intensity in terms of the maximum intensity at the waist. There's this factor here of how the thing diverges out, and then there's this, so the maximum intensity is on the angle, and then the intensity falls off like this Gaussian as we go out. So this is for beyond the Rayleigh range, it looks that. Otherwise close in, or this would be beyond the Rayleigh range, it's falling off like that one. Okay, and if we want to find the area or the fraction of the optical power, this is pretty much true in general, not just for a Gaussian or a Gaussian beam. Is that if we want to find out the average power, it would be the amount going out to some annulus divided by the total. So again, we find out we get something like 86% of that power is within the 2 sigma points of the beam. Okay. So again, that's something like, and here's our example coming back of the helium neon laser, a reasonably realistic example. Why does this thing, still getting this straight. So at any rate, let's say that the maximum irradiance is this. Let's find the power and irradiance of this helium neon laser beam, a 5 milliwatt helium neon laser. That's a pretty standard helium neon laser operating at 6333. Has a spot size of like 1 millimeter. Find the maximum irradiance and the axial maximum irradiance at 25 meters from the laser. This is a problem we did before, an example that was in the last section of the chapter. Again, plugging in just brutally for the waist, we're saying that the waist is 1 millimeter. We find out that the maximum irradiance or maximum optical intensity is something like 1.2 watts per centimeter squared, okay, at the waist, because that's a small waist, so we get a reasonably, well, it's not really a high intensity. If we think about high intensity, would be a gigawatt per centimeter squared or something. A watt per centimeter squared is not especially high intensity. these days, like, it used to be before the laser pointer that you actually see surveyors and such would be out in the field using helium neon lasers. These days, pretty much you can do anything you can do with one of these helium neon lasers with a red laser, which is made out of aluminum gallium arsenide, essentially. Essentially, one of those laser pointers is some kind of, is essentially a flash. There's like a flash tube inside of there, and there's a gallium arsenide crystal. Then in the middle of that you pump to inversion, and then you polish the edges of that crystal. And that's enough actually to get a beam if you have before, okay. So again, it looks like a typical solid state laser. And it's amazing how cheaply they can make these. So this would be something like the gallium arsenide. And here. And then this is essentially all that's inside of those laser pointers. The green ones, though, you have to double the beam. There, essentially, you use a gallium arsenide laser that's at 830, and you actually double the beam wave, or actually use a neodymium YAG crystal inside of those, and then you have a beam doubler. It's amazing how cheaply they can make those. If you pull one apart, everything's integrated into essentially a single crystal with the optics integrated into the same piece. So I don't know, do people still use helium neon lasers? I know I still have some in the lab, but they're relics, actually. I don't know. Do you all use helium neon lasers in your labs?
Fortunately.
What's the reasoning?
Calibration.
Hmm?
Calibration.
Calibration, because it's an atomic line. Okay, and then the aluminum gallium arsenide laser is a function of the room temperature. So if you want to have an absolute calibration to an atomic standard, then you know what the helium neon is, because the temperature coefficient is really small. Okay, good. So it's for frequency calibration these days, no longer for surveying. So at any rate, this is the kind of maximum intensity we get in there, something like a watt per centimeter squared. Just for comparison, a watt per centimeter squared, generally in nonlinear optics, to see any kind of nonlinear optical effect, you normally assume you need about 100 megawatts per centimeter squared before you get any onset for any kind of nonlinear optical effect. Just as a comparison there. And again, the Rayleigh range we can calculate for this, if you have really a millimeter is big, again, so the Rayleigh range is pretty big. It's 1 million wavelengths, which makes sense. You figure if you have a millimeter and you square that, you've got about 1 million wavelengths. So you divide that by lambda to get your angle, and it's like microradians. So you expect that you're going to have about a meter type Rayleigh range. If you have a meter Rayleigh range, because that angle is about a microradian, well, again, you'd expect about 20 millimeters if you go out 25 microns at that microradian angle. And again, the irradiance at the beam axis going out there is about 3 milliwatts per centimeter squared. So it's very, very, well, it's low. It's not low compared to eye safety. Actually, that's why they rate lasers like that, as we might know. Probably there are other people here who know even better than me, but if you look at the sensitivity of the eye, it has a huge peak around 510 and falls off, but is still pretty sensitive at 6328 at the helium neon range. This kind of intensity would be fine in the IR. One of the reasons why 1550 nanometers was chosen for fiber optics is that at 1550 nanometers, if you have several milliwatts in the fiber core, it's eye safe. That was one driving decision. Another one was dispersion. Although there are arguments for going to 1310 for dispersion. But at 1550, you can have several milliwatts, and as long as it's expanding at a reasonable angle, there's no eye safety requirement whatsoever. Whereas in the red, this would still be dangerous, and this could be quite damaging in the green to the eye. That's also the reason why green looks brighter. The same kind of brightness in the green, the same beam intensity, looks brighter than do other colors. But that's actually the responsivity of the eye rather than the eye damage threshold. Okay, let's talk about Snell's law. Enough on beam intensity for the moment. So we have Snell, Willebroord Snell, who was Dutch, and people say that he experimentally discovered the law of refraction in 1621. He didn't publish it, though. It was Descartes who published it after the death of Snell, who I do believe, died in 1626. And Descartes published it around 1637. People, I guess, kind of know that it's Snell because apparently, as they ask here, Snell's law or Descartes' law, I guess Descartes didn't actually say where he got it from. He just kind of published it, but people were aware that Snell had done this. Snell, I guess, worked with some of the astronomers in Holland and was reasonably well known. There was a lot of astronomy going on at that point. If you look in, for example, the Feynman lectures, that ancient book now at this point, he has a chapter that's on principle of least time. And he went and looked up, and apparently Ptolemy had measured all the measurements that Snell had made in the year 100. And there's a chart of that. Ptolemy published 3 scientific books. Ptolemy was had studied with Aristotle, actually. No. It was what's his name? I have that wrong because Aristotle was 2 or 3 centuries before that. Ptolemy was born in Alexandria, which is now in Egypt, but it actually at that point was a Greek colony. It was a Greek colony, though it was taken over by the Romans, so even though Ptolemy spoke Greek and was of Greek origin, he lived in Egypt and was a Roman citizen. It was Alexander the Great who studied with Aristotle. Alexander the Great is the one who set up Alexandria, now that I think back on those things. But Ptolemy lived from about 90 AD till, I don't know, 160 AD or something. And he was one of those first Greek philosophers who published scientific work. And it wasn't based totally on skeptical type guesses, but he actually had experimental data. But probably Snell was not aware of that, so we aren't going to assume that he stole the data from Ptolemy. We'll assume that he actually worked it out. Ptolemy, though, did not work out an equation. He had the measurements, but I don't think anybody knew about trig functions in the year 100 AD. But apparently Snell and Descartes both knew about trig functions, and they actually worked out one of the first physical laws in history that had ever been worked out, where you actually wrote down a law and it had predictive behavior, because you could predict it as the change in the optical properties. So Snell's Law looks something like this. In the book, he's generally having the light incident from below. I'm used to having the light always incident from the left, so I put in a few of my own slides from here, and you'll see mine are incident from the left and his are incident from the bottom, but you'll just have to live with that. So this is what the problem looks like. If we were to illuminate a surface, like say, for example, a glass plate, a surface between air and glass, we'd have an incident beam. As we know, if we have a glass plate, a beam's reflected off of it, and a beam's going to be transmitted. And these are the kind of things that we'll use. We'll use theta I for the incident angle. We'll use Ki for the incident K vector. Use Kt for the transmitted K vector. Calling this one N2, we'll call this one N1. If we're in free space, N1 is evidently 1. If we're in glass, N2 is evidently, well, I don't know what it is evidently. If it's fused silica, it's 1.45. If it's borosilicate glass, it could be 1.7. Depending on what we have. Some lead zirconate glasses are up around 1.8, actually, even higher than that, depending on what you want. But generally in books, people use 1.5 because it's an easy number to work with. And I guess that isn't too bad unless it's a really special glass. And we'll talk about incident and transmitted angles. So he has a construction here in the book on how you can derive this. I thought I'd use what I think is a little bit easier way to think about this. This is from my own notes, but let's say we had an incident wave. Again, we've got theta I, theta R, theta T. And if we look at the phase fronts over here of each of those waves, so again, we have incident phase fronts, or these guys coming down this way, and then the reflected phase fronts will be coming off this way, and the transmitted will be coming off at a different angle. We could break this problem up into the X problem and the Z problem. So we've got phase fronts coming along Z. Well, those phase fronts coming along Z, they don't have to be the same on both sides of the Z-axis. But the ones that are coming along X, if we think about them, those phase fronts expend on both sides of the interface. So the phases of all the waves have to be progressing at the same rate. So if we wrote for the incident wave that it were something like e to the I kz cosine theta I, e to the I kx sine theta I, and we wrote for the reflected wave it were I to the I kz cosine theta I, e to the minus I kx sine theta R. We wrote for the transmitted that it were e to the, and I should probably put ones on here, e to the ik2 cosine theta 2 z, e to the ik2x sine theta 2. We see immediately from equating this one, and that one, we have that. They have to be, otherwise these phase fronts would be different on the two sides, and there'd be no way that you could equate it. The phases have to be the same, the two sides of the phase front. I think that's the same argument that he has in the book on saying that the waves have to add up coherently or they don't add up at all. Okay. So this just comes from these guys over here. from the phases having to be the same on the two sides. They don't have to be the same on the two sides over here because these waves are only for negative z, these are only for positive z. In order to solve this problem, we have to use the group velocity and equate the powers going into the interface and away from the interface. And that's called Fresnel's problem. And that's how we get the coefficients of reflection and the coefficients of transmission. The directions, though, they come from Snell's law. To do the power equation, we have to use something more. Okay. Now, the other thing, well, let's see if I've got that on the next one. Oh, yeah, and then in general, if we had like lots and lots of these interfaces, as he mentions in the book there, this is true for every one of those interfaces. It's also true even if the material's continuous. If you had a continuously varying index of refraction, n of z, that n sine theta, so this could be n of z sine theta of z equals a constant. And this is also, we sometimes call this a ray tracing variable, or we call it an invariant of paraxial ray tracing. Actually, it's even beyond paraxial. It's an invariant of ray tracing. If you put in a ray at an angle, it times the index will always be a constant. And it can greatly simplify some nasty looking problems in trying to do optical design. Okay. And that's, again, can just be solved the way that I did it previously. The problem with that when n is a function of z is the problem of equating the power in and the power coming out becomes very, very complicated on finding the actual reflection coefficient of that. Although not too hard in one dimension, it has a solution called a Riccati equation, which can actually be done. So enough for Snell's law. So anyway, this just summarizes what I just said, which relates the angles. And now the next thing we want to look at is, so we just talked about the case where, for example, we were going from free space to glass. This could be glass. And then when we go in, it bends towards the normal. If you go into a higher index, always the rays will bend towards the normal. But then the converse has to be true. If you're going from less to more, then the rays bend away from the normal. They go at higher angle coming out. Now over here, nothing can go wrong here. No matter what angle I choose, there's always a ray coming out. That's easy enough if we're going to a more dense medium. Over here, if I'm going to a less dense medium, there's going to be an angle that I come to where the angle coming out goes to 0. And now that's okay when it still goes to 0. That just means that we drew that. That means we're doing something like exciting a plane wave in the plate, okay, or in the cladding or something over here. When we come to this so-called cutoff angle, which we say is N2 over N1. So for air going to glass, this would be something like sine theta c would be 0.6. Sine theta c of 0.6. I don't know, what is that, about 60 degrees, something like that. It starts to get to be a reasonably high angle. If we're talking about something like, let's say that we were a gallium arsenide laser or semiconductor laser, indium phosphide, name a semiconductor, not silicon, we can't make a laser. So like, let's say that this is semiconductor gallium arsenide. Gallium arsenide, the index is something like 3.5. So if this thing here is like 3.5, we have 1 over 3.5, then that turns out to be reasonably small. We're talking about 15, 20 degrees. Practically anything above that will be totally internally reflected. That's also one of the reasons why when you have semiconductor lasers, you don't actually put mirrors on them. The reflection, as we find out from this, is something like 40%, and you aren't losing many rays because rapidly they get damped. If they get off axis, they get trapped. So the actual cleaved semiconductor itself makes a pretty good laser cavity if you can cleave these things pretty cleanly. Cleaving silicon is a lot easier than cleaving gallium arsenide or indium phosphide. If you try to cleave indium phosphide, it kind of breaks like a clot of dirt or something. It's nasty to get the cleavage plane right. I'm glad I don't do that for a living. It's very hard to do. But at any rate, gallium arsenide isn't so bad. Silicon is very easy to cleave, but of course you can't get inversion because it's a direct gap. Okay, so then with that, so that's the total internal reflection angle. So again, we could talk something about this. This is what the meaning of it is. The angle's higher. At some point it goes there, and at some point there's no wave at all whatsoever. There's nothing going along the interface as you go higher and higher above it. And again, let's take a look at a picture I have. Okay, so this would be something like solving for the angle. So when you go above this, you find out that the reflection angle becomes complex, or becomes actually purely imaginary. I guess the only point of this slide is if you keep plugging things through the equations, despite the fact the angles are imaginary, you still get answers. As it turns out, as is so often the case, the answers are still correct. They look funny. You have to be a little bit careful to interpret them, but they still are meaningful. And you find out that what happens above looks something like this. If we had an incident phase front coming in like this and a reflected phase front coming out, what happens on the other side is that there's nothing propagating along the interface, but there is light inside of here, and that light dies exponentially with distance into the medium. But there is energy in there, and that energy is oscillating back and forth at the optical frequency. Depending on what this index is and depending on how great you are above the internal reflection angle, this can be significant compared to a wavelength. So you can get significant penetration into that. The waves are damped, but they're still there, and they have a phase front that's going along in this direction. So that is what it means. There are a large number of things that we actually can use this for because of this fact that there is energy on this side. So let's take a look at a few of them while we go through here. So applications of TIR. This would be just a general prism over here. So if we go through a prism, we'll have two angles of deflection over here that are causing dispersion, wavelength dispersion, because the index of the prism is a function of wavelength. So evidently, all of us who've played with prisms, you put the thing up and you can get a rainbow out of the prism over here. But also, depending on the index of the prism and the wavelength of the light, you can use that prism to reflect light. like that. Why would you want to do that? Why wouldn't I just use a mirror?
You can adjust the beam length and the path length difference because it goes through a different medium.
That's one thing. Yeah, you can adjust the path length, and we'll see another application of that in a minute. How about a more general question? Why would you use a dielectric stack instead of a mirror?
You get higher reflectivity and less loss.
You get less loss. It's not really so much higher reflectivity. The mirror is pretty good, but what doesn't get reflected warms up the mirror. I can remember one of the first PhD theses committees I was on here, actually it was with Dana Anderson's group. One of the guys was putting together mirrors, this is a long time ago, but one of the guys was putting together mirrors for the LIGO experiment, or analyzing the mirrors for the LIGO experiment. And in that experiment, apparently, at least what they thought at that time was that a single absorption event would be enough to move the fringes enough that you'd miss a gravitational wave. So they were worried about single absorption and what that would have, the back reaction that would have on the surface of the mirror. So it would be better there to lose the photon rather than absorb the photon, because if you lose the photon, you get phonon production. Whereas if it were lost, if it got transmitted, no problem. It doesn't cause any oscillation that would compete with other oscillations inside of the system. So at any rate, that's a reason. But also the path length, I think I've got another example of that, although not worked out in detail on here before too long. Applications of TIR2. Yeah, here we go. This is, I think, called Fresnel's rhomb over here. So this is a more complicated than a prism, but it's a piece of material. It's a prism-like piece of material, low loss. And if you come in with 45-degree polarization and you pick the angles right, of course these things will have an aperture at the input and an aperture at the output, you can turn 45-degree polarized light that you line up at the input into circular polarization. And it's an extremely low loss polarizer, also extremely expensive. There are ways you can, these days now with, I don't know, fiber optics and other things where we try to do things, putting in a bulk component that costs thousands of dollars seems insane. But there was a time when these things, and there are systems where these things are reasonable. But this can be very low loss. Again, you can anti-reflection coat the input and the output facets, and you can get like near 100% throughput on this thing of highly polarized, accurately polarized light. And it's broadband because it's using TIR. It doesn't matter if the angle's off, if the wavelength's off, it doesn't affect it very much. It's highly insensitive to that. You can think of all kinds of other ways to go from linear to circularly polarized, and they're first order sensitive on the wavelength. So you have a little bit of a shift in the wavelength and it gives you ellipticity. This one doesn't because it's TIR. This one's first. Okay, another example over here would be, let's say we have lower index on the inside, higher index on the outside. Or excuse me, just the opposite, higher index on the inside, lower index on the outside. This here could be a glass plate, and this could be this here could be a candle, a flame at the end of it. And actually it's claimed that the ancient Greeks knew about this, knew how to do wave guiding in plates of glass, although the first publications on it, I think, go to a guy named Daniel Colodon, who was Swiss, I think from Geneva. Also, we'll mention him later here as we go on. I think he was the first guy who did this for doing another type of experiment. where he guided inside of a higher medium. This also is an optical fiber, evidently. In an optical fiber, what we do is we dope the core dope the silica core with a little bit of germanium to raise the index of refraction. And these things evidently will guide for like hundreds of kilometers. Here's a picture of one in 3D of a step index fiber. Graded index fibers guide a little bit differently. Graded index fibers are much better for dispersion. I think there's a problem for that on your next problem set, which is posted on the web. So here's a picture of a fiber and a detector, a little fiber optic link on here. So again, total internal reflection is the basis of that. And it can be low loss. Inside of a glass plate, it's not low loss. Again, glass has loss of on the order of a dB per centimeter, so you don't have to propagate very long. There's not much light left. An optical fiber, though, at 1550 nanometers can be 0.2 dB per kilometer, so you can propagate 40 kilometers and still it looks almost as bright after 40 kilometers. It's only down by about 8 dB. Not even an order of magnitude. Some other things, this kind of prism has all kinds of different names. Everybody's put their name on it. I can't remember all the names. I call it prism coupling myself because I can't remember whose name. It depends on the field. Also, solid state people call it different things than optical people call it different things than fiber people. But if you want to couple into a waveguide, this is a real problem also. Like here we show this end face of the waveguide as being nice and smooth and wonderful. Let's say that this were a polymer that we put on top of a glass substrate or a silicon substrate. That end won't look like that, I guarantee you. You spin the polymer on and this end face, this stuff won't go to the end. You'll try to cleave it and you'll shatter this part down here and you'll melt this part over here. You never get a good end face. And that's true of many different materials, many different processes. You can't cleave through both materials the same way. So the only way you can actually couple light in is from the top. What you do here is if this N1 of the prism is greater than the N2, there's always going to be an angle where this projection of this is going to be the same as that one on there. And it's total internal reflection. And if you get right at the TIR angle, you'll excite a wave going along here. So this is a way of exciting exotic waveguides over here. And you can do the same thing here. You can make multiple materials, and this is the way that directional couplers are made in optics. By calculating where that angle is, you can couple light from one waveguide to the other waveguide. And directional coupler is a pretty standard component both in microwaves as well as in optics. That's the way that we couple light between different channels. Here's a lateral displacement example. Evidently, if we put light into a plate from here, it's going to be refracted at this surface and be refracted again. And if we look straight through here, we'll see things at the wrong position. Just like the idea of looking through water. If you look through water, the refraction at the surface will give you things at a different position, effective position. And again, this is just worked out in the book just to show that this is one of the effects of that refraction off a plate. So again, here, rather than go through that, you can go through that in the book. I thought I'd come to the last pretty picture here. And I like this. And this comes back to this guy, Daniel Colladon. Actually, that's spelled wrong. That's supposed to be an O, I'm almost sure, in his name. And this is guiding light in water. And apparently Colladon was the first one to do this, except he had an experiment where he was guiding inside of something like a plate, and he was trying to show other people he was guiding inside the plate, and people couldn't see the light, so they said, "You're crazy, you don't know what you're talking about." So then he poured water over the end of the plate and showed that the light came out at the end of the water stream, and he did it by chance. He didn't care if it was guided in the water. He was trying to illustrate it was guided in the plate, not in the water. It was Tyndall saw the experiment, so he published this in about, oops, where did that go? Come back. There we go, there it came back. Okay, so Tyndall was the first one to actually do this. Anyway, Colladon published this in, I think it was 1842. People thought this was more interesting. The effect here where you had one container, you lit up the container with green light, you could see it propagating through here. Colladon, one of the other things that he was famous for was he then ran for the mayor or Bürgermeister or whatever. Actually, it's in French, if Geneva is French speaking, but anyway, he went on the city council of Geneva, and he was the guy who got gas lighting put in on the streets of Geneva in 1844, which was the second city in Europe. I think Paris was the first around 1820. So he was also known for light for that. But Tyndall was the first one to actually do this experiment. And that experiment became very popular throughout the late 1800s. This was, there were many different demonstrations of this at the exhibition in Paris in 1889. They actually hooked this up in fountains. They'd have big fountains, and they'd find intense sources, and you'd see the light going through the fountains. So anyway, I thought that was an interesting sidelight that you can guide in water. And again, here they're using bubbles in order to make it whiter. Okay, that actually is about what I have for today. As I've mentioned, there's another problem set that's posted, problem set 2 due next Tuesday. I'll assign 4 of you to work problems in class. When we do that, it'll be my plan. If you could get me your slides, I'd say the night before, but if you send them the night before, then I'll be able to load them in the morning. So as long as I have them by 7 or 8 in the morning by the day of class, then that will be fine. And then I'll let you have 5 minutes, no more than 5 minutes, to kind of outline how you solve the problem. And otherwise, that's about it, if there are no questions.
What day would it be that we present? Thursday or Tuesday of next week?
No, 2 will be assigned on Thursday, 2 on Tuesday. Okay, so there'll be 2 every day. And that way we can break up these 75-minute lectures into nicer pieces of like 25-5, 25-5. Does that add to so? No, that's too long. Anyway, something like that. So at any rate, see you on Wednesday or Thursday.
Dr. Mickelson?
Yeah.
Controllers for like.
Yeah.
It's like a power step or something.
Okay.
Revive the current.